Hello everyone, welcome to my programming club. Today we will be solving the problems of weekly contest 364. Now let's move towards the first problem of the contest. So you are given a binary string s containing at least one. You have to rearrange the bits in such a way that the resulting binary number is the maximum odd binary number that can be created from this combination. So return a string representing the maximum odd binary number that can be created from the given combination. Note that resulting string can have leading zeros. So basically, if you are familiar with the binary representation of a number, then you can easily solve this problem. Every odd number will have one set bit at its 0th position, 0th binary position. So this bit should be set in every odd number, since it represents 2 raised to power 0, which is 1, and all other places represent powers of 2, so it will not give you odd number. So you should keep one for this 0th place, and rest of the ones can be used to place them as far as possible. For example, let's say 1, 2, 3, 4, 5. A 5 length string is given to you. And now let's say it is having only 2 ones and rest 3 are zeros. Let's say what you will do, you want to have a maximum number. So these places represent the powers of 2. So you want to place your one should be compulsorily placed here. At least one will be used. So we are remaining with only one. So where to place it? It can be placed at a position which will give us maximum value, which will be 2 raised to power 4. So you can place it here. Remaining 3 zeros can be placed here. So number will be looking like something like this. And you have to return this string. So let's have a look at the implementation. So what you will do is, you will be constructing your string in this manner, in this direction, right to left. At last, you will return your reversed string. Actually, count the number of ones. One of them will be used for the 0th position. Now you will count the number of zeros. Subtract number of ones, since you have already used one. Now you will append number of zeros, these zeros. After you have done appending one, so now you will append after that you will append ones. After that and remaining ones. At last you will return the reverse string. This is how you will be solving this problem. Let's try to submit it once. As you can see, it's getting accepted. So let's move towards the second problem. So the second problem's name is beautiful tars part 1. So you are given a zero index array of maximum heights, array named maximum heights of and containing any integers. Your task is to uh, you are tasked to build n tars in the coordinate line along the x-axis. The ith tar will be built at a coordinate I and has a heights I. So after configuring the towers, let me basically explain it in my own words. So this array will be given to you, maximum heights. What you have to do is you have to construct another array. This will be maximum heights array. You have to construct another array, heights of same size. Both of them will be of size n. And what you have to do is you have to make this array a mountain array. What I mean by a mountain array is it will be something like this. Let's say this particular index is the peak index. So all of the indices that will be on its right and left can be either equal to it or lesser than it. This is the array which will be a mountain array. So whenever there will be a single peak element and all other elements on its left and right can either be equal to it or lesser than it. Similarly, for each of the element, all of the elements can on its left can either be equal to it or lesser than it. So similarly in this way, I hope you are able to understand. So a mountain array should be created, and there is a restriction that, let's say, this particular index will not be considered in your mountain array. So your mountain array will be going from here to here. And if at a particular position 3 is there, then you cannot place a number bigger than 3, which is 4. You can either place 0, 1, 2, and 3. So these are the restrictions. You can also see the restrictions here. So for index 1, to the very last index, you have to follow your heights array should be following this particular pattern. So it cannot be 0. From 1 to max heights, your heights value will be in between these two values, 1 to a particular index I, let's say max heights. Heights is a mountain array. Array is a mountain array if following conditions are satisfied. So you can read the conditions. You can see the elements an index I such that following condition satisfies. Basically, if you consider ith index as your peak, then all of the heights from 0 to the ith index will follow this range, and all of the heights from ith index to very last index will follow this range. So let's have a look at the constraints. So the constraints are not very much large. So we can have a n square solution. N square solution will require at max 10 raised to power 3 into 10 raised to power 3 equals to 10 raised to power 6, order of 10 raised to power 6 operations, which are lesser than order of which are lesser than 10 raised to power 8 operations limit. Here with this number of operations limit, I will be providing a link for an article describing, let me quickly change the slide, how the time complexity of accepted solution varies according to input size. So this is how you will be approaching the problem. Actually, the approach is yet to be discussed. So how you will be approaching? What we will do is we will consider each index to be peak of mountain array heights and calculate. Basically what you have to return is maximum possible sum of heights array and calculate maximum possible sum of array. Accordingly, you will be doing modifications in this maximum heights array. Basically, what you will do is you will consider each of these indices consider each of these indices to be candidate peaks and calculate heights array sum basis for each of these candidates. So let's have a look at the implementation. For each index in the, this is the max height array. I have named it according to myself. You can replace it. So I think it have ruined the code. I think you will be able to understand. This is the max heights array. For each index in H array, which is max heights array, Consider that index as your peak. And calculate sum of heights array that will be formed accordingly, and return maximum sum possible for heights array. So you will find the maximum sum. What you will do is, for every index on the left side of max index, or say peak, you will height at that index to given for a mountain array in the program statement. Similarly, for every index, similar thing you will do for every index on the right side of current peak index, which is max index. At last, you will return the sum of the newly formed heights array. So this is how you will be solving this problem. At last, you will return your maximum sum possible. So let's try to submit it once. As you can see, it's getting accepted. So it's not the best runtime, but in part 2 we will be optimizing it. In part 2, what happens is, the problem is same, only the difference lies here is that the constraints have been increased. So the number of, you cannot apply n square solution here, it will give you TLD. So this particular size of the heights array is increased. So we will be applying a different approach here. So let's move towards this problem. This is the third problem of the conquest. For implementation of this particular program, you should be knowing two concepts. Basically, a single concept is required, which is the use of monotonic stack. Are new to this concept. Basically, link of two problems, two standard problems of monotonic stack will be provided. Article explaining those problems, and then you can run the use of monotonic stack. It is nothing special. It is just a stack. The way of using stack is something different than we regularly use. So you should check those two links before proceeding with the solution. So they will be next greater element and the previous greater element. So instead of greater, we will be searching for the next smaller element and previous smaller element. So what we will do is, let's move back towards the board. This array, let me clear. So I think let's kind of, if let's say you will do the same thing, consider, let's mark the indices. Each index to be candidate heights array. But instead of running a loop in O n time to convert this array into a mountain array, what you will do is, let's say you decide to pick this particular index to be a candidate for height peak, something like this will be formed. So if you consider this element as a peak, and if you know what was the last index on its left hand side that was smaller than that was having value smaller than this current value is 4. What was the index at which the value for this particular index, what will be the index which is having value smaller than 4? So for this is the index that is having value smaller than 4. On right hand side also you will check for the same. What is the index which is having value smaller than 4? It is that this index. For example, let's say instead of this particular index, there was something like this 4, 5, and 3. And instead of this one, let's say there is 7, and then let's say there is 2. So the indices, this index is considered to be the current candidate for peak. Indices will be 0, 1, 2, 3, and 4. So the index on the left hand side of 4, which is lesser than 4, is this index, and the index on the right hand side of this index, which is lesser than 4, which is having value lesser than 4, is this index. So to maintain this mountain condition, this particular condition, you cannot use a number greater than 4 here. So it should be the maximum number that can be allowed here is 4. So if let's say you convert these two into 4s, then your array will be a mountain array. So after converting this particular number into 4 and this one into 4, you will be using two arrays to store the left hand side sum, which will be including 4 to the very left, 4 and all the numbers to the very left, and then you will the array right hand side sum, which will include all the elements which are used in the heights array, which is now a mountain array. So the modified array will be looking like something like this: 3, 4, 4, 4, and then here it will be 2. So two different arrays will be formed now. One will be this and another will be this array. For each index, these two arrays will be available. So the sum of heights array will be left hand side sum at a particular index. For a particular index to be considered, let me quickly write here. Particular index here candidate for peak of heights array the sum of that heights array will be left hand side sum at this particular index plus right hand side sum at this particular index. This is right hand side sum, this is left hand side sum. Left hand side sum. These will be two arrays storing these two sums for each index. And this will be right hand side sum. The value of height, max heights at that particular index. Why we are subtracting it? Because it is counted twice, once while using the left hand side array and once while using the right hand side array. So we are subtracting it once. So this will give us the overall sum. And to find the indices, previous smaller height index and this one next smaller height index. For these two, you will be requiring monotonic stack. Links that I will be providing you for monotonic stack. These two links you should explore. Then you will be able to understand the solution. Now let's move towards the solution. So firstly, what we will do is you will find first of all for each index in max heights array, you will find what is the previous and what are the previous and next indices having heights smaller than that of height of tower at current index. So it can be find out using monotonic stack. For this purpose, you will be using monotonic stack. Pardon me if some spelling is incorrect. I hope it does not affect your understanding of the approach and solution. Next stack will be used here. Once you are done finding, this will be for finding indices of previous smaller height. And this particular one will be for finding indices of next smaller heights for each index. So here you have to, I will again request you, if you are not familiar with the use of monotonic stack, please explore these two links, then you will be able to understand. So next what we will do is, then you will store this, you will make these two vectors for arrays. Left hand side sum and right hand side sum. Then you will find the, you will populate the values of in uh, left side sum and right side sum arrays, which will help you to find the height of sum of heights of heights array in case of every candidate index for peak of heights array. So what you will do is, for the current index, left hand side sum of the current index, you will find the number of equal height towers that should be there. So in this particular example, the number of equal height towers on the right hand side, left hand side are these, and on the right hand side they are these. How you will be getting those values? Value of current candidate index minus the index of previous smaller height tower. It will be the number of equal height towers that you can allow. So, and the sum of the heights will be number of equal height towers into the height of current tar. So it will be the left hand side sum. Similarly, in similar way, you will be calculating your right hand side sum. I have made the code as much as verbose as I would have done. So understanding this particular section of the code, please ask your doubts in the comment section. Then what you will do is you will consider each of the index in heights array as your candidate peak, and then calculate the height of sum of heights of height array. The current height sum for the current candidate index candidate peak index. Current height sum will be left hand side sum plus right hand side sum minus the max heights index. Why? Because this particular index is counted twice. Once in the left hand side sum, once in the right hand side sum. That's why we are subtracting it once, so that it should not be counted twice. So I hope you are able to understand, and then we will return the maximum height sum. We will keep updating the values of maximum height sum possible. So at last you will return maximum height sum. Let's try to submit it once. As you can see, it's getting accepted. So that's how you will be solving this problem. Now let's move towards the last and the final problem of the contest. The problem's name is count valid paths in a tree. So there is a undirected tree given to you. This kind of tree will be given to you. Nodes will be labeled from 1 to n, and here is, let's say, 5. So nodes will be labeled from 1 to 5. You are given an integer n and a 2D integer array of edges. So edge will be representing, so this 2D array will be containing edges. So for example, if there is an edge between 1 and 2, so it will be represented as, let me quickly take another slide. So in edges array, it will be a 2D array. So let's say a edge between 1 and 2 exists, so it will be representing something like this. And let's say edge between 2 and 5 exists, so it will be represented something like this. You can consider this as first node and this as second node, so they will be connected. And this edge will be bidirectional edge, so you can either go in this direction or in this direction. So it will not have any particular direction, so it will be undirected. This is the meaning of undirected. So it's mentioned here also that each vector or say array in this 2D array will represent something like this. So the nodes U and V will be having a edge connecting them. So you have to return the number of valid paths. So it is defined what a valid path is. A valid path is a path which is starting from any one node to another node, and the number of prime numbers in that path is exactly 1. So for example, let's take this sample input as our example. So if you take this particular input as your example, a valid path can be 1, 2, and 4. So in this path, between 1 to 4, you are having only one prime number, which is 2, which is exactly one prime number in this path. So this path is a valid path. Another valid path can be this path from 1 to 3. This path is having only one prime number, which is 3. So it is a valid path. I hope you are able to understand what a valid path is. You should not think that valid paths should be existing in this direction only. For example, let's say consider this example. 1, 3, 4, and then 2 and 5. Now this is also a valid path. Let me mark the path. This path from 3 to 4. It is having only one prime number, which is 3. So this path can also be possible. So what the problem statement further says is that the paths, let's say you counted the path as 3, 4, then 4 and 4 to 3 will be the same path. So it should not be counted twice, only counted once. So let's have a look at the constraints. So these are the constraints. So the number of nodes in the tree will be of order 10 to the power 5. So, and the edges length will be 2. So 2 nodes will be there in edge, and the input is generated such that the edges represent a valid tree. So the tree is a valid tree. So what you will do is the prerequisite for this particular problem will be disjoint set union. Link for this particular article will be provided to you. You should be familiar with what a disjoint set union is and how to implement it. Only then you will be able to understand the solution. So I hope if you are not familiar with, you will go through this link, and then you will approach towards the solution. Now let's see how we will be solving this problem with the help of disjoint set union. Let me clear the board. Yeah. So what you will do is, or let's say, let me quickly explain it in the code itself. This particular implementation is a standard implementation of disjoint set union. Basically, if I give you a brief idea what disjoint set union does is, it will form groups of nodes. Let's say in one group 3 nodes are there, in another group there are 2 nodes. So group 1 of these nodes will be picked as the representative of the group. And similarly, one of these nodes will be picked as the representative of the. So, disjoint set union for forms group, something like this. So what we will do is, uh, after writing the implementation for disjoint set union, another topic that you should be familiar with, I forgot to mention, is sieve of Eratosthenes. This particular algorithm or say approach is used to find the number of prime numbers from 1 to n in this particular time complexity. So a basic implementation of this particular algorithm will be used. So you should be familiar with it, because you will be needing to check whether a number is prime or not. You should be able to do it as much as fast as possible. So that's for that we are using sieve of Eratosthenes. Eratosthenes. His name is difficult to pronounce. So this will be used for checking whether a number is prime or not. Basically, you will be able to check it in of one time, but to build this particular sieve, you will be requiring this much time complexity. Where n is the number of numbers that you will be looking for to check whether they are prime or not. So you will declare a disjoint set union. Then you will form the graph according to the edges given. Uh, According to the edges array, this particular array, you will be forming bidirectional edges. What I mean by bidirectional edges, let's say there is an edge between u to v, then you can go from u to v, or you can go from v to u. This is a bidirectional edge. All these edges are bidirectional edges. I hope you are able to understand. That's why we are making connections from u to v, and then from u to v to u. So once you are done forming the graph, then you will use your the disjoint set union that you will just you have just declared. First of all, what you will do is you will be forming a chain or a path. Instead of chain, you can say path. Without prime numbers in it. So for if a current node is a prime number, then you will skip it. Else, if that's not the case, then you will check for all the neighbors of that number or say node. Which are not prime. So basically what you are doing is uh, let's say something like this is there. Four and six. So let's say you consider this as your current node, and for this particular node, uh, how many neighbors are not prime? This is a prime number, so it will not be considered. So this two will be considered. So two separate paths can be considered from this to this. Let me choose another color. These two separate paths can be there. This I should mention that this path will not be having any prime number as of now. Are not having primes as of now. Okay. Then you will form these paths, path without primes. Then you will attaching prime numbers to the path without primes. At different places available, different nodes available in that path. Let's say path was there 1 to 6, 1 to 6, and I have a prime number 3. Let me quickly represent it in another class. So 3 can be attached either to this one. This will form a path. Path will be 316. Or it is not direction. So 316, 3 to 6. Say 6 to 3. Another option, you can attach 3 to 6. This will form another path, which will be 1 to 3 or 3 to 1. Whichever you may like, they will be counted as one. Similarly, these two will be counted as one. It's mentioned in the program statement itself. See, mentioned something somewhere like, yeah, path A and B and A to B and B to A are considered same and counted only once. So this is what we will be doing. We will be attaching prime numbers to different nodes available in the non-prime paths. So if we will consider a node if and only if it's a prime node, we will consider a node only if it's a prime node. So initially the number of node primes will be set to 1. Why it will be set to 1? Because all the nodes which are neighbors of a prime number are one node actually. Let's say with the prime number 3, following neighbors are connected: 1, 4, and 6. So the number of prime nodes, if I consider this particular path, the non-prime nodes is 1. It is 1 for this particular path is 1. So initially node primes will be 1. So considering those paths which are attached to a prime number, those neighbors you can say or paths. So if the current neighbor is a prime number, then we will not allow it, since two primes are not allowed. take here. Two paths, two prime numbers are not allowed in a path. So if that is not the case, then your answer or the number of uh, what they say valid path, you can say this is the number of valid paths. Will be number of node primes into the size of its neighbor of union. Basically what happens is, let's say initially there were three node primes and there is a prime number let's say 3, and a number 4 is attached to it. I know how many number of node prime numbers are attached to 4, or how many number of non prime numbers are in uh, are in the same group with 4. How many number of combinations can be made? Let's say it is number of node primes that are in the including 4, same group with 4 is x, and number of node primes that were earlier there will be y. So how many combinations? X into y. So I hope you are able to understand. So this is what we are doing. Then the number of node primes will be increased. So y will be increased to, y's value will be y plus x now. So number of node primes will increase since we have found a group that is now having more node primes. So initially I told you, let's say it is 1, 3, 4. Now these two numbers are there in a group containing 1. Let's say 1 is the representative. So two numbers are there. And then further number of node primes is, let's say these are two node primes. So accordingly, you will be able to form different paths, and the number of node primes will increase, which will be 2 plus 2 now. It will be 4. It's mathematics here. So then you will return your number of valid paths. So this is how you will be solving the problem. If you are still having any doubts, please feel free to ask them in the comment section. I will be more than happy to answer them. So thank you for watching. Before ending the video, let's try to submit it once. As you can see, it's getting accepted. So for this particular portion, you should be having knowledge of distributed set union, DSU, and C operator things. So that's all for my side. if you are having doubts in any of the questions, please feel free to ask them in the comment section. Thank you for watching. Thanks.